my name is Deval Mehta and UTME is here to present our research on mass spectrometry. First of all, I would like to introduce our team. Our team mentors are Harsh sir, Professor and AICHE ma'am. My team members are Abhishek Sharma, Archit, Ashlok Kumar, Himanshu Singh and Sai Jaswanth. So let us start our presentation with our abstract. Our project aim is to analyze the composition of gases and particles in space environments using mass spectrometry to enhance our comprehension of celestial bodies and investigate astrophysical phenomena. Our research till now is based upon the types of planetary mass spectrometer, investigation of surface composition of planetary bodies, monitoring spacecraft cabin air quality, mass spectrometer using Apollo mission, ion confinement in 2D and 3D ion trap. Let us know what is mass spectrometry. Mass spectrometry is an analytical tool useful for measuring the mass to charge ratio of one or more molecule present in a sample. It is a vital tool used in different scientific areas. There are 4 types of planetary mass spectrometers. First, magnetic sector mass spectrometer. These instruments were flown to examine the atmospheric composition of Earth by way of high altitude rockets. These mass spectrometers have been used in various missions like Apollo 15, 16 and 17. Quadrupole sector mass spectrometer. This mass spectrometer is used to separate ion with the help of direct current and radio frequency electric field. Third, time of flight mass spectrometer. Time of flight mass spectrometer helps us to analyze flight time of ion that have been accelerated to a uniform kinetic energy. And the last one, ion trap mass spectrometer, which is used to capture and analyze ion across a mass range through a combination of electric and magnetic field.
I am here to explain the ion confinement in 2D and 3D ion flux. Researchers have addressed a crucial challenge in two-dimensional array of trapped ion for quantum information processing. They achieved rapid reloading by introducing a continuous flux of pre-cooled neutral atoms from a distant source. This approach allows fast loading of a single ion per site, maintaining long lifetime without disrupting neighboring ion quantum bytes. This method meets key criteria for extensive array loading, crucial for large-scale quantum information processing. Notably, the loading rate can be further increased by loading ions in parallel, requiring only additional photoionization layer power without additional atomic flux. In ion confinement within a 3D quadrupole ion trap, charged floor planes are captured. The classical setup involves a particle with positive charge held within the trap. The surrounding cloud consists of similarly charged particles. The electrical field shown in blue is created by a quadrupole arrangement of intercaps and a ring electrode. These schemes illustrate the confinement mechanism where the electric field effectively traps the positively charged particles, showcasing the principle of quadrupole ion. This is all about the 2D and 3D ion confinements in ion traps.
Mass spectroscopy in planetary surface exploration. Mass spectroscopy in planetary surface exploration. Mass spectroscopy plays a key role in exploration of planetary bodies by providing vital insights into their surface composition. This technique is employed on the landers and rovers to analyze the elemental composition of the surface. Its primary objective is to identify chemical composition and to understand the geological and atmospheric condition of the celestial bodies. Ionization techniques such as laser ablation, electron impact, and thermal desorption are used on the collected samples obtained through drilling and scooping or scraping method. The resulting ions are then characterized into mass analyzer, providing a detailed mass spectrum. By examining these mass spectra, scientists can draw conclusions about geological history, potential habitability, and overall composition of the celestial bodies. Use cases: SAM on Mars Curiosity rover, MENCA on Mars orbiter mission, and LIBS on the Vikram lander. Monitoring spacecraft cabin air quality. Mass spectroscopy is involved in ensuring the safety of astronauts by monitoring spacecraft cabin air quality. Mass spectrometers are integrated into life support systems to detect contaminants such as carbon dioxide, trace gases, and volatile organic compounds that may risk the health and safety of the astronauts. It offers high sensitivity and rapid analysis capability, ensuring early detection of any contaminants. This continuous monitoring allows for the early responses to change in air composition and ensuring the corrective measures can be implemented before time.
Our research also covers the mass spectrometer of the lunar Apollo flights 15 and 16. It was used to measure composition and distribution of the ambient lunar atmosphere. It was employed redundant tungsten filament, 2 small heaters consisting of ceramic blocks with embedded resistors on either side of the ionization chamber. Now I tell about the use of mass spectrometer as a gas analyzer for metabolic and physiological experiments. On orbit, physiological measurements were obtained to verify crew health and in-flight performance. The trend of limited medical studies on orbit continued through the Apollo program, with collected medical data concentrated on understanding the physiological responses that would have the greatest impact on crew health and safety.
Let's take a look at Orbitrap mass spectrometer. The Orbitrap is widely used in analytical chemistry and bioanalytical research. The Orbitrap mass spectrometer is known for its high resolution and high mass accuracy, making it a valuable tool for identification and quantification of wide range of compound in various samples. If we talk about the working of Orbitrap as shown in the figure, there is a central electrode structure which is at very high voltage surrounded by a red container called as graphic. This denotes the ion population that is moving axially around the electrode. The fixed movement generate ion current which further proceed using Fourier transform. Space probe or sample return missions could collect material from celestial bodies such as comets, asteroids, or planets. An Orbitrap mass spectrometer could potentially be used to analyze the chemical composition of these samples, providing insights into the origin and the nature of these celestial bodies. And it can help us in decoding the cosmic phenomena of the events happening in the universe. This technology can be used in India's future space missions like Mangalyaan-Gaganyaan, a space mission towards a human flight exploration, and once that happens, we will be able to look at space station building in subsequent modules. The engineering challenges in space application of Orbitrap is to reduce size and power requirement. This can be encountered by utilizing microfiber techniques such as electromechanical systems, polydimethyl siloxane, and accelerometer to miniature various components of the mass spectrometer. Incorporate state-of-art of electronics and signal processing technologies that are more power efficient, using lightweight and durable material that can help reduce the overall weight of the instrument.
Now let us see the application of Orbitrap mass spectrometry. The Orbitrap mass spectrometry is a powerful analytical technique used for the analysis and characterization of biomolecules including proteins, peptides, nucleic acids, and lipids. The Orbitrap mass analyzer developed by Thermo Fisher Scientific is known for its high resolution and mass accuracy, making it well suited for a variety of applications in the field of proteomics, metabolomics, and structural biology. Now let us see the overview of Orbitrap mass spectrometry in analysis and characterization of biomolecules. In protein and peptide analysis, where the high resolution and mass accuracy of Orbitrap analyzer enabled accurate peptide identification by matching experimental mass spectra with theoretical spectra generated from protein sequence database. In PTM analysis, where it helps in distinguishing between different isomeric modifications and increases confidence in the identification of modified peptides. In glycan and nucleic acid analysis too, and in structural biology, where Orbitrap mass spectrometry can be used in combination with other techniques such as mobility spectrometry to study protein structures and conformational changes. That was all about our process flow. Our future research plan include analysis of biomolecules that have been discovered in the atmosphere of Moon and Mars using Orbitrap mass spectrometry, and analysis of small molecules and structural elucidation using Orbitrap mass spectrometry. That's all. Thank you.